Hi everyone, and welcome to the first Fathom Insiders webinar, which is the first, which will then be held quarterly moving forwards throughout the year. I'm James Bridges, and I head the customer success team with Fathom. So I'm really excited to join you in this new initiative. We're really giving you the opportunity to get the inside track on what Fathom is up to, and also an opportunity for you to hear from our experts on questions that you've been asking us. So it's a free to join program if you are a Fathom customer. So please do extend the invite to any of your colleagues who may not have been able to make this call or didn't get the initial invite. Yeah, you will be able to register via our customer hub. In general, in these sessions, you'll be getting an update from either myself or one of the members of my team on recent and upcoming product releases, as well as a more detailed look into our future roadmap and what we're planning on building. As well as this, you'll hear from our experts. So we have a big team of experts with Fathom. You will hear from those, and they will be addressing questions and concerns that you've raised to us. Really, the aim is that over time, the content of these sessions will be shaped by the feedback we get from you, our members. So in terms of what we're covering today, I will be giving that update on our roadmap and update on some of our products. And Dr. Natalie Lord will be discussing recent views from scientific literature on climate scenario modeling and taking you through what you should be considering when selecting a climate scenario for your use case. Following that, Anthony Cooper, our senior hydraulic model developer, will be giving you some guides on how to best present the Fathom data and how this can be used to communicate flood risk effectively. As I said, while we've selected these initial topics based on previous questions we've had and topics we found interesting, the aim is that the future content will be driven by our members. So at the end of this session, there will be a questionnaire that will pop up. If you have any topics you want to learn about in these sessions, please drop them in there. Alternatively, do feel free to reach out to either the customer success manager for your account or myself with any suggestions you may have. So moving on from that, we'll look into our products. So two main product updates that we've had recently. Global Flood Cap 1.2 was an update to, as you expect, our global flood cap model. The main addition here was building in our global climate dynamics framework into this model. So this gives you the ability to model any region globally for flood, not only for the current climate scenario, but any realistic climate scenario this century. So this is a really powerful tool and should support you in with future risk assessment and climate-based regulatory reporting requirements. On top of this, we've added support for disaggregation across additional postcodes, mostly in the US, Canada, Mexico, as well as adding event metadata. This is a really useful source of information which provides additional information about each event within the model. There's a page dedicated to this patch on our customer hub. You can search for it, and the link to that page should also be in the chat. On top of that, we're about to release a patch to our US and global flood maps. This is fixing a number of kind of localized issues that have been highlighted by our clients. Again, more details of that are available on our customer hub. In addition to those localized changes, we're also aligning and correcting some issues with the permanent water mask, which is also embedded within that product. In terms of a timeline, we're looking to really roll this out throughout August. We've taken delivery internally, and we're in the process of updating all our systems with the data. So your customer success manager will be reaching out soon to give you more details of how you can access the updated data. On top of this, we'd also like to share in these sessions a much more detailed view than you may have received previously of our roadmap. So this is kind of our indicative product roadmap moving forward, kind of over the next 18 to 24 months or so. It's indicative, so I can't guarantee that any of the dates shown here we stick to, but we will do our best to kind of follow this timing. Your feedback, as always, is essential to us in shaping this roadmap. So if you're seeing products or services here that kind of aren't meeting your needs, please do let us know through the various channels that you can connect with. As mentioned previously, the main release for us this year has been Global Flood Cap Climate, the 1.2 update. In tandem, we've been working with our colleagues in Swiss Re to enable access to our data through various platforms that they own. RDS and POI are two of those, and they both have access to Fathom's data, which is yeah, a great enhancement. We'll also see a patch to our global flood map data, as I mentioned, and that will be followed by an update to our global terrain data product in kind of Q4 this year, so towards the end of this year. The core of that product is Fathom Dem. You may have seen that that was recently released for academic use. The main enhancement we need to make is take that already world-leading DEM, combine it with LiDAR where we have it, make that full terrain data set fully available for you. So that's the work we're completing now, and that will, as I say, be available towards the end of the year. Then there's a bit of a gap. Within that time, we're working hard running all the simulations for updated global flood maps. So Global Flood Map 4 will be kind of released towards the end of next year. We're not going to sit around and only do that at the moment. So we'll also be doing iterations to our API service, our existing main products, so our Global Floodcat and Global Flood Map products. They'll go through kind of continuous kind of smaller scale improvements, but they will be worked on as well. And last in our current plan is our update to the Global Floodcat. So following the update to our underlying hazard maps, we'll update the CAT model to rely on that improved view of hazard. So that's kind of really pushing out towards the end of our timeline here, around 2027. And then finally, the most major update I think I'm going to share here is that there's been a recent decision within Swiss Re, and that moving forward, Fathom data will be underpinning their internal view of flood risk moving forward. So that will have some impact on our roadmap and the products that we will look to release together. But that's a really exciting update, and we'll share details of that moving forward as we get them. So that's it from me. I'll hand it over to Nat, who will take you through discussion on climate options.
Thanks, James. So yeah, we all know that we're living in a non-stationary climate. Global warming is already altering climate and extremes, including flooding, and this will continue to worsen in the future unless strong global climate action is taken. And because of this kind of future risk of climate change, we provide a range of different climate options with our products. Next slide, please. So at Fathom, we've developed climate dynamics, which takes future changes in extreme rainfall, river discharge, and sea level, and incorporates the impacts into our flood and catastrophe models. And this tool allows the assessment of flood risks for any subperil, any plausible climate scenario, anywhere in the world with uncertainty. And climate scenarios can be based on a year, combined with either a global warming level between 1 and 5 degrees C compared to the pre-industrial period, or an emissions scenario such as the SSP, RCP, or NGFS scenarios. And so uncertainty in the projection is represented in the form of percentiles. Next slide, please. So this plot shows the range of emissions scenarios that we can provide at Fathom. So we have time to the end of the century on the x-axis and global warming level on the y-axis in degrees C. And so this is the change in global average temperature relative to the pre-industrial era. And you can see that there's a few different sets of scenarios that we can provide. So the SSPs, RCPs, and NGFS scenarios are shown by different line types. So whether there's a dash, a dot, or a solid line. And then within each of those sets, there are a number of different individual emission scenarios, which are shown by different colours. And these range from scenarios with relatively low greenhouse gas emissions and warming of around sort of 1.3 degrees C, up to scenarios with high emissions and high warming levels approaching 5 degrees C. And I'm going to talk about these different sets of scenarios in the next few slides. But just to note, we can also provide scenarios based on global warming levels. So if you're interested in a kind of Paris Agreement style scenario of 1.5 or 2 degrees C, for example, then that is also available. Next slide, please. So this slide shows the products that our climate dynamics is available in. We have our flood maps, so it's available in the global flood map and the US flood map. We also have a slightly different version of climate dynamics in the UK and the Japan flood maps, which include a more limited set of scenarios, and these are based on regional climate model data rather than global climate model data. But the full climate dynamics for these countries is available through the global flood maps as well. Our risk scores are a simple but kind of powerful set of flood risk metrics. These were developed as part of our global flood map, and they allow users to really easily compare the flood risk for assets across a portfolio under different climate futures. And finally, our global flood cap model with climate dynamics was launched last month, as James just mentioned. And this allows users to quantify the impact of climate change on flood hazard and also potential losses. Next slide, please. So a common question we get, as you might imagine, is which scenarios should you choose? Because there are obviously lots of different versions. And there isn't really a right answer on this. It somewhat depends on what your use case is, how far into the future you're interested in, what your view of risk is, amongst other things. The main thing we would recommend is to consider more than one scenario, since we don't know how future greenhouse gas emissions and associated warming will evolve. But during this webinar, we're going to give a bit more information and guidance on the different scenarios that we can provide. So hopefully it will provide a bit of clarity to you. So for example, if you're performing a standard risk assessment or scenario analysis, you may choose to select scenarios from the broadest set that we provide, which underlies several of the other sets anyway, and these are the SSP scenarios. Next slide, please. So SSP stands for Shared Socioeconomic Pathways, and these are IPCC scenarios, so that from the Intergovernmental Panel on Climate Change, and they were used in the latest assessment report, the sixth assessment report. And these were essentially developed by climate scientists and economists and energy systems modelers to examine how global society and demographics and economics and energy systems might change over the next century. And there are 5 SSPs in total, which you can see, well, 4 of them anyway, the 4 main ones on the left-hand side. And these all make different assumptions about those things that I mentioned. And then within each of these, there's a number of different scenarios that kind of fall within them. But there's 5 key scenarios that are generally used, and these are the ones that are shown on the plot on the right-hand side, along with historical observations of global warming. And these scenarios range from projections with lower warming, which is shown in blue. So these assume a more sustainable future and are associated with low challenges to mitigation and adaptation. There's the more sort of middle of the road scenario shown in yellow, with more medium warming and medium challenges to mitigation and adaptation. And then there are the high emissions scenarios with high warming, which are shown in red. And these are associated with high challenges to mitigation and adaptation. I also mentioned the RCP scenarios a couple of slides back. So these are the representative concentration pathways. And these are the previous iteration of these SSP scenarios. So they were used in the 5th IPCC assessment report. And they're broadly similar to several of the SSPs, although with some differences in kind of the evolution of warming over the next few decades. Next slide, please. So as an example of another use case, financial institutions are increasingly being put under pressure by regulators and investors and consumers and other stakeholders to identify and assess and mitigate the possible risks arising from climate change. So if you're responding to regulation, for example, carrying out climate stress testing, then it's likely that the regulator will have specified which scenarios you should be considering. Next slide, please. So one examples of scenarios that can be used for climate stress testing are the NGFS scenarios, which were developed by the network of central banks and supervisors for greening the financial systems. That's what NGFS stands for. And these are a set of scenarios that have been adapted from the IPCC scenarios, which aim to provide a current and up-to-date reference point for understanding how climate change or physical risk and climate policy and technology trends known as transition risk could evolve in future climates. And they aim to essentially help central banks and supervisors explore possible climate impacts on the economy and the financial system. So at one end of the spectrum on this plot, you can see we've got physical risk low to high on the bottom x-axis, and then transition risk low to high on the y. So at one end of the spectrum, we have the orderly scenarios, as they're known. So these assume that climate policies are introduced early and become gradually more stringent, and this results in relatively low physical and transition risks. And then at the other end are the scenarios where no additional action beyond current policies are taken, or it's taken too late to halt significant global warming. And these scenarios result in severe physical risk, including some irreversible impacts. Next slide, please. So another example of regulatory requirements include the Climate Biennial Exploratory Scenarios, or CBES, which was the name of the Bank of England's first exploratory scenario exercise on climate risk carried out in 2021. And the CBES scenarios build on the NGFS ones and define a set of years and associated warming levels that these banks and financial institutions were asked to assess risks for. And as part of CBES, the UK's largest banks, life and general insurers, and Lloyd's syndicates were required to assess the impacts of physical and transition risks of climate change. Another example is the EU taxonomy. So this is a classification system which establishes a list of environmentally sustainable economic activities which financial institutions are encouraged to align their portfolios with. And it includes criteria for mitigating flood risks, such as investing in flood defences and sustainable water management systems as well. Next slide, please. When you're picking scenarios, you might also decide to take into account some of the latest scientific research. For example, by selecting scenarios based on which are thought to be more or less plausible, depending on current climate policies that have been or may be implemented. Next slide, please. So this plot shows warming projections based on current policies and commitments compared to the full AR6 SSP range of warming projections. So again, we have time on the x-axis and global warming level on the y-axis. And under current policies, climate models suggest a median future warming of 2.7 degrees C in 2100, with a 5th to a 95th percentile range of 2.3 to 3 degrees C. So this is represented by that kind of orangey colour bar. It should also be noted that current policies represent something of a moving target. Obviously, like policies and technology just change through time, so these projections will vary as time goes on. But broadly, this is where they were, I think, in 2021, I think the study is based on. Projections based on climate action commitments are also shown. So you can see the yellow bar shows the 2030 nationally determined contribution commitments, and then net zero commitments are shown in blue. And you can see that they show lower levels of warming at the end of the century than current policies, because they assume additional action on climate change. But you can see that the range of warming covered by these three kind of sets of projections cover approximately half of that of the full range of IPCC AR6 warming, so those SSP scenarios. And most of the reduction is seen at the high end of the warming range, but there is some reduction in the lower range of warming as well. Next slide, please. So there's therefore been a little bit of a move away from these very high-end emission scenarios in the scientific literature. And this is partly because these scenarios assume that current and future energy production is dominated by coal, whilst in reality, the world is generally transitioning away from continuing fossil fuel expansion. The latest IPCC AR6 report stated that high-end scenarios have become considerably less likely, but cannot be ruled out. So the sort of SSP 5.8.5 and to some extent SSP 3 7.0 worlds would require the active reversal of past progress. So the kind of currently implemented policies would have to be reversed. And so it's thought that that's generally quite unlikely. So their main use now is thought to be sort of high-end, high-risk scenarios. And estimates of future emissions and future warming under current policies tend to most closely match the sort of middle of the road SSP scenario, so SSP 2 4.5. And you can see on this plot that's kind of that sort of 2.5 to 3 degree warming based on current policies is thought to be sort of the most likely at the minute. But as stated, the kind of high-end scenarios can't entirely be ruled out, even if they are thought to be less plausible. And there are other uncertainties in the sensitivity of the climate system to greenhouse gas emissions, which do mean that they may still be useful if it turns out that the climate system is more sensitive and has higher warming to greenhouse gas emissions than our climate models predict or than we might have thought. The paper that is shown on this plot in this slide as well also did a survey of IPCC or some IPCC authors and concluded that there's also skepticism among these authors that even that central 2.7 degrees C estimate of current policy outcomes will be achieved. So apparently more than half of the authors that were surveyed expected at least a 50% chance of reaching or exceeding 3 degrees C by or before 2100. So there is still a potential use for some of those sort of higher warming scenarios, particularly if you've got a more conservative view of risk and want to kind of look at the not worst case scenario, but the kind of real extremes and what those changes could be. Next slide, please. So as I said, which scenarios you should choose, it really depends on your use case, how far into the future you're interested in, and what your view of risk is. But hopefully that's provided some helpful context and some helpful information about the different scenarios that we have available and which may be most suitable for your use case. As you can see from the plot, many of them are loosely paired across the different sets. So SSP 5.8.5 and RCP 8.5 are very similar, for example. So they show similar trajectories and end of century levels of warming. But yeah, as I mentioned, standard practice is to go for two or more scenarios, including a sort of lower and a higher warming scenario, just to account for some of those uncertainties in future developments and emissions, to make sure you're kind of covering the high end of risk and then the lower, more optimistic end of what the risks might be. Next slide, please. Any questions? I think is what we will move on to next. So yeah, if anyone has any questions, please put them in the Q&A box. If anyone would like any more information on climate dynamics and how it was made, and also how it's integrated into the global cap model, then there are some links on these slides. And obviously, we're always happy to talk about climate scenarios. So if you are struggling to decide which ones to use, then absolutely get in touch and we can have a bit of a discussion about it. So we've had a question from Megan asking if the slides will be made available after the webinar. I imagine so. This is being recorded and will be available on our website, I believe. James may, yeah.
Yeah, I can take that one. So yes, we will make these slides available, and the recording, as Nat said, will be available through the customer hub, so you'll be able to watch back as well.
Thank you, James. Cool. Well, it doesn't look like we've got any questions. If anyone thinks of anything, please feel free to just put it in the Q&A and we can always pick it back up after the next section, or just get in touch via our website or email if there's anything longer you'd like to discuss. But yeah, otherwise, I will hand over to my colleague Anthony. So he's going to talk about some of the ways that you can visualize flood map data. Thanks, everyone.
Thanks, Nat. So we get lots of questions asked by people, how we get and sort of how we look at our data, what we do internally, how perhaps they can look at our data. So we generally provide our data. We don't generally visualize our data for our clients. We're going to talk through a few of the things that we do in-house, of how we look at our data, how we try and look at it in the most effective ways possible. So we can skip into the next slide. So we provide our data, our flood risk data, as essentially just a big grid of numbers, whether or not you get it through our API or through on-prem. It's just a series of little squares, each of which has a little number in it. And that number for our depth data release represents the flood depth in centimeters. If you just look at it as sort of numbers and points, that's not very clear. But you can start adding color to it. When those numbers go greater than 0, that's where the flooding is. And that's the sort of first stage of giving us our flood map visualization. On the next page, please. But you can do a lot with those color ramps and what you do with those colors. And adjusting the range of your color ramp particularly can change your perception of what the flooding looks like. If you have a very, very small color ramp, so very little sort of difference between the biggest and smallest number on there, everything looks consistent. The same thing if you go for a really, really big range on your numbers. Again, everything ends up looking consistent just because it all gets pushed to the top or bottom end. If you get those numbers somewhere in the middle, that's when you start to sort of see differences and you can really start to pick out in certain locations where is really deep flooding, where it's probably going to have more hazard, and where is it sort of a little bit less deep, where it might be sort of less of a problem, and just helps you really understand where those differences are and how the flood sort of interacts over the floodplain. Next page, please. And we at Fathom, we produce three different perils maps, one for fluvial, covering the larger river flooding, one for pluvial, covering surface water and sort of more rainfall flooding, and one for coastal. And all three of these have very different characteristics as floods. Fluvial and coastal, these are generally bigger, deeper floods. Whereas pluvial, this is much shallower floods than most of the time, covering sort of more sort of surface water and that very shallow flooding. But it covers much more of an area. This means we often want different color maps over different areas. So again, we've got 4 color maps here. Again, if we just have a very small color range in our color maps, it all goes that sort of single pink with a 5 centimeter one. We push up to that really big range, the 1,000 centimeter, again, it all just sort of get pushed around. But this time we want sort of smaller numbers, so perhaps 5 to 50 or 5 to 100, and you can really then start to pick out the areas of high depths and more concern and the areas which are probably less of a problem. Next slide, please. And different color ramps can make really, really big differences to people's perceptions of flood risk. The typical assumption is the more standout, that could be a brighter color, a darker color, or more vibrant, a color that really draws your eyes to something, that's going to be the area of higher hazard. So we at Fathom often use this sort of this paler blue up to this really bright, vibrant pink. And that bright, vibrant pink really draws the eyes to it, and that's obviously where the high hazard is. If you go for that sort of rainbow effect, you end up with these sort of this sort of both sort of with a shallower color in the middle. People risk getting drawn to both the shallow flooding and the deep flooding, but not sort of that bit in the middle. This is really confusing to the eye, and you can see that in the top right-hand image. And if you invert your color ramp, again, this can change your perception. Bottom left looks like all the flooding's right in the middle, whereas bottom right clearly shows much better where the sort of key area of depth is. That sort of dark color really draws it. There's different ways as well of picking those colors. You can pick colors that match your organizational style. So again, in Fathom, we do a lot with these pinks and blues. This is just kind of what we do, and that sort of reflects across our brand. But you should also think about things such as accessibility, making sure that the colors are going to be accessible to all your users. So particularly thinking about color blindness, where often reds, greens can quite often sort of blur to certain people. So really try to think about how you can sort of pick a color range that doesn't sort of cause problems with that. And I highlight this really good paper that we'll share around, where it's trying to encourage people to move away from rainbow color ramps for reasons of accessibility, and reasons of sort of displaying the data clearly. Next page, please. The other thing you can do, instead of just going this sort of smooth ramp, actually banding the colors can really make it sort of clear, and it can give really clear links to real world hazards. Many areas in the world have sort of very good definitions. In the UK, the Environment Agency quite often will define sort of when it becomes a risk to property and how much of a risk to life it is, and sort of define bands of when it sort of steps over. I know in reality, actually, it is all a little bit of a sliding scale. It doesn't suddenly change to just being a risk at this particular point. But actually, sort of splitting your map down into these certain bands really enables you to target certain locations and understand where the biggest problems are. And it gives you a point to sort of focus on. So again, here it's the same map on both sides. It's just very different sort of looking, and there's very different perceptions that you're trying to raise here, and how we're sort of matching those. And you can see those red areas clearly and going, oh, that is definitely the area we need to focus on. Next slide, please. The other thing we find that's really important working with our flood map data is what you put around the flood map data. a really complex or often uncolored and busy base map can really distract from the data that you're trying to show. Um, so in this case, where we really, really want to highlight the flooding and the flood map data, it's much better to have this much cleaner, much grayscale background to really try and focus on the flooding. Whereas on the left-hand side, it sort of gets lost into the background of the rest of the mapping there. Next slide, please. The Fathom data also uses something called a permanent water mask. This is to cover up the areas which are always wet, the main bits of rivers, lakes, and the ocean. Depending on what you want to show in your map, depends on how you want them to display this. So we use a value of -32767. And most sort of GIS softwares will let you sort of play around with what you want that to be. So on the left-hand side, we just set that value to our highest flood depth. And that gives a really, really good looking picture because it kind of merges into the rest of the flood map as you expect it to. On the right-hand side, however, we use a completely contrasting color. So we set the permanent water to black. This then helps us really identify where's actually a flood risk problem and where is just a lake. So when you can zoom out, actually going that area, yes, there's clearly a flood problem, but in many areas it's not actually as bad as you think it is because actually it's just got a lot of lakes and a lot of watercourses in this region anyway. So it's really trying to understand where's flooding and where's just wet as an area, particularly when you're viewing at larger scales. Next slide, please. There's also different ways of sort of showing the risk of flooding. So instead of showing the depth for a single return period, actually combining return periods together, and you can use different banding. So you might just choose to show flooding over 30 centimeters together. And research has shown often this is actually easier for users to understand. If they know at that point, they can go, okay, is that 1% risk of flooding at this point here? Is it 10% chance of flooding? They can just look at one single map and go, is there a risk of me flooding really, really quickly? And how likely is it going to happen in a single year? So again, it's using very similar sets of colors, but this time it's just flipped around. And again, it's the pink areas. That's a really high risk. It's going to flood really regularly. Once you're getting out to those blue areas, it's less of a problem. It's going to happen on these sort of much rarer return periods. Next slide, please. And we can also combine flood data with other data to generate information and graphics specific to a location. So you can combine it with things such as property data sets, and then you can just assign the flood map it data to those particular properties. So rather than showing an entire area of flooding, you can really clearly then see what properties have really got this problem. And again, you can do it in different ways. You can do it based on likelihood of flooding. So again, you can pick the properties out really these are the properties that really need sort of focus, or they're the ones that are much higher risk to price into insurance pricing. And then we can also look at in a particular event, how badly is that property is going to be impacted. So we can pick the properties that are going to be sort of, we're showing on the right-hand side there, the properties on the 100-year event, the ones that are get really, really badly hit. But then also highlighting the ones which are only going to have perhaps almost nuisance flooding, where it's perhaps not even reaching the threshold, and actually it might just be around the outside of the property. So it's really good to understand using it and combining it with other data sets. Next slide, please. And often you do want to combine it with complex data. The flood in Fathom, we love flooding, but it's not always the key bit of information. So sometimes it's worth simplifying the flood data down to something else. So here is some data that we've produced looking at flood risk within Dar es Salaam, where actually we also really want to show of what's the population density, because it's really important to understand people. Flooding is a thing that impacts people, so we need to know what the people are, how many there are, and where the key areas of population are. So in this case, we've simplified the flooding down to just this little hashing, which allows us to see where we've got a flood risk. But then we put the population data in there as well. So we can then start really picking out the dark colours, the really important colours here, are actually the areas where there's going to be lots of people. There's going to be a huge population density affected by flooding, as opposed to it's got really bad particular flooding there. So we understand where the flooding is, but we also understand the sort of the other risks and hazards that's combined with this. And this helps us really paint an important picture of how we look at flood data. Next slide, please. The final thing I'll come on to is water surface elevation. So we talk a lot about flood depth data, and that's one of our key products, but we also produce a water surface elevation data set. So flood depth data, that's the depth of water above ground level at that sort of local location. Water surface elevation is the flood depth above a defined datum. So think of it like sea level. this gives you some very different approaches of how you can sort of show off flooding. And it's also useful for other tools, particularly when you're looking at infrastructure, um, water levels control, floodplain management. Water surface elevation is often the sort of more useful, understandable sort of tool here. Next slide, please. When we visualize water surface elevation, it looks really, really different because it's above this sort of datum. Um, and generally in an area, the water surface elevation across that area will be a relatively smooth transition. So we can see on the right-hand side, over this large area, we've actually got this transition where this water level above this datum height changes from 50 to 40 over many kilometers. But it's a very, very smooth sort of no sort of jumps within that picture. Whereas the depth map on the left-hand side, the ones we've been showing through most of this presentation, they're constantly changing up and down between 0 and 2.5 and even deeper areas. Um, it's trying to show different things and it gives you different options of where you want a smooth water surface elevation. It's a really useful plot, particularly if you're then starting to put infrastructure and other things against it. So we just look on the next slide. We can start to see if we're using water surface elevation, we can combine this with terrain data sets and we can really start to pick out where the problem areas are. So we can see in each of these little valleys what the water level is going to be in those valleys. And that's aligned with our elevation data set. And this shows us, particularly if you're trying to plan your road or you're trying to plan your railway, what it sort of changes, how it's really important. So in that lower image, you can clearly see that actually the area covered by these larger events grows significantly because we sort of go outside of these little valleys and start covering these much larger areas. So as you can pick that up on the 2D maps and the depth maps, it really, really helps sort of stretch it out across larger areas and provides this sort of smooth profile that's really clear to do. Which then, if you're trying to plan particularly sort of things like linear infrastructure, roads, railways, it gives you a really powerful way of sort of understanding this data and provides a much better assessment of risk, particularly where the heights of the assets you're going to be putting in and the elevation of the assets is known. Next slide, please. The very final thing we can start doing, once we've got this water surface elevation data and we've got this terrain data, so in Fathom, we have Fathom Plus as our this terrain product. This enables us to sort of stretch the world around. So we don't just have to look at this sort of 2D world, we can start looking at 3D mapping. It's a really, really nice way of conveying what flood risk looks like in the real world. And we've started seeing some of our clients doing slightly more cool things of using things like VR goggles, where you can really start to see where the flooding, what it looks like. But using the water surface elevation data sets really starts helping to plot it. And actually, you can combine all three terrain data sets here together. You get your terrain data set, your water surface elevation data set, and then your depth data set. You use the terrain data set to define the whole world, so you stretch out those satellite images. Use the water surface elevation data set to then sort of apply the flooding across that world. And then we use the depth data set to start coloring that flooding. So we can then sort of see where those high depths are, how it all fits in and merges with the rest of the world. If we go on to the next slide. So that's hopefully a little bit of an idea of how we sort of build our flood maps and sort of look at the colours and how we sort of then use this to evaluate them. And hopefully how some of our clients can help also use that data. And we'll be happy to take on any questions based on that. It doesn't look like we're having many questions, so perhaps I might just hand back to James here.
Yeah, thank you, Anthony, and Natalie both for taking us through those topics. So that really leads me to say thank you for joining our first Insiders webinar. On the screen now, there should be popping up a questionnaire. One quick question, if you let us know about any topics that you'll be keen to hear about in future webinars, and we really look forward to discussing those with you in the future. So wishing you a good rest of your day and rest of your week, and we will catch up soon. Thank you.